Hey, this is our second presentation. So without much ado, I'll start it up. We're about 5 minutes late. Okay, so here we go, and then I'll show up after.
Hello, I am Jamal Hadi Salim. This talk is a result of work that was done at Bloomberg by Nabil Bitar and myself over a few months. It builds on the performance analysis effort described in the previous session that you may have attended, or you can look at the slides after. The title was Linux ACL Performance Analysis. The focus of our effort is driven by desire to get better performance. And I'm going to provide an upfront warning that this is a very packed and a little fast-paced presentation. I could easily have fit this into at least an hour's worth of presentation or more even. The performance analysis talk from earlier should complement this, of course. I'll go over several fronts here. One is the design, our goals, the semantics we ended up with, and I'll spend a good chunk of time afterwards on the challenges encountered and resolutions. And this is more fitting to eBPF, which is what we ended up choosing for our first incarnation of this. So what is policy tables? It's a minimalist alternative to the famous trio of IP tables, IP set, contracting, and the concept of IP table rule sets with groupings of IP addresses using IP sets, complemented by contracting for caching and statefulness, has been very widely deployed, is very widely understood, and for that reason, we adopt that trio. From now on, I'll just use this term trio to imply IP tables, IP set contracting. I'll use it interchangeably. So like I said, our current implementation is purely eBPF based with a user space control plane API. Our motivation, yes, the $ plays a big role. Performance. A friend of mine who works for a large cloud vendor that should remain nameless, in many discussions I've had with him, and I'm saying, like, who cares about you saving this 1% you're touting here, or 2%? And he claims every time I do that, I'm saving my company $1 million. And I used to scratch my head around this, but with this experience, finally makes a lot of sense to me. So I'm glad to get this opportunity to do this. The photo here shows Grace Hopper. She's holding what is equivalent to 1 microsecond. That's 300 meters of fiber. So you incur a cost of 1 microsecond. If this was a horse race, you just lost by 300 meters. I know I'm exaggerating a little bit there, but I hope the point is taken that the cost of a single microsecond has a lot of impact. So I'm going to go over the design goals here and approaches we took. Just a quick reminder of where XDP, ETC, and eBPF, you can look at this slide after. I'm not going to spend time on it. Policy goals, policy table goals, the design goals relative to IP tables, again, performance, high throughput, low latency, that magical combination for both the data path and the control path. We wanted to go for minimalism and flexibility. So just use only what you need and don't incur the cost of the extra features that exist. Extensibility, yes, our starting point is the trio, but we want to innovate beyond that in the future. Usability, we're very happy if Ptables is understood by what we would call the trio craftsman, the craftsman who understands IP tables, IP set, and contracting. I'm going to spend a little bit more time on this slide here because it's fundamental to our design. This is an abstraction. I should just put a disclaimer that this is merely an abstraction. We'll go into the details of implementation later on. I've seen a lot of studies which claim that they have suddenly solved the IP tables performance problem by having 3 or 4 eBPF tables. It doesn't work like that, folks, in the real world. In the real world, you still have to have linear iteration. Whether you think that's a cool thing to do or not, it's a necessary evil. You may have overlapping rules, overlapping prefixes with different priorities, etc. And the only way you can solve that is if you can't have overlapping addresses in LPM. LPM, for example, it selects the highest prefix that matches. So what we have here is essentially semantically equivalent to IP tables. So IP table rules, linear iteration, IP sets as the LPMs, IP set net to be specific. The multi-port, I think, match for IP tables is essentially used as the abstraction here for single list or a range of ports. The contracting essentially sits on the cache table over here. So what we have is when a packet comes in, if the cache was enabled, then the first thing you do is you look up the cache table, and should it fail to find anything there, this is an exact match lookup. With direction and the port attached being part of the key. And then if it fails, you then linearly iterate until you find a match to which you add an entry to the cache table. On a failure, you basically end up hitting the default rule. Where do these ports get attached? Where do this abstraction get attached? It gets attached to one or more ports, and the TC wall, this will be equivalent to the control ports. Sorry, to the TC control block, the block control feature. You attach it to one or more net devices. The grouping of the subnets is essentially semantically equivalent to, let's say, saying I'm going to attach this to engineering subnets. Likewise on the LPM, you could express it into things like all internal subnets. The groups of ports are essentially mapped to applications. So you say, I want to match all the Postgres databases, which could be one or more ports, depending on how you've configured your setup. We have explicit priorities. So essentially, you can actually, unlike IP tables where the rule sets are implicit, you can add rules and have gaps between the rules, so that later on you can attach. You can add rules in the middle where there are gaps, and this is important for the control plane performance, as well as for management, where you can add and remove priorities, and that's how you'd probably update rules. From a perspective of wildcards, it's possible to have missing LPMs. LPM table, like you see, this rule set has a missing source destination IP, whereas this one has a missing destination IP. Another important detail in this is we keep path flow accounting. So the cache, everything has to be cached, and when it gets cached, there is a control plane interface that grabs this table on a periodic basis, or it could be asynchronously out of the kernel based on events that happen in the kernel, that then sets it to some analytics engine somewhere. Okay, I hope that I can go into those more details, catch us later on at a table, maybe after this talk. I went over this, so you can read the slide. Is essentially what I just said, so we'll skip this one. I'm going to go over the performance goals. Again, I want to emphasize this because it's primary objective of our effort. We want higher throughput, normalize over CPU and latency for both the data path and the control path. Our initial implementation is based on eBPF, but we want to say it upfront that we're not restricted to eBPF. We will use whatever necessary infrastructure as long as it stays within the constraint of using the Linux kernel. It's not outside of the Linux kernel perspective. For example, if offload is required, if we have to use P4 as long as it matches, it's integrated into the Linux kernel, we'll use that. If we have to use some other kernel feature, hell, even if IP tables improves performance, that's where we're going as well. But just we're not. It's not a religious war between eBPF and IP tables. We're saying that our goal is to improve performance, and that's where we're going with this. Extensibility goals. If there was a hardware offload, for example, the craftsman, the management person, the ops guy should not have to worry about what the constraints are in hardware. If it can take only 10 rules versus 10 million, if it requires slightly different semantics, that abstraction has to be taken care of underneath. Flexibility, I think this probably does justice to this. As the Burger King commercial says, have it your way. Yes, this is the problem with, for example, no offense intended, but IP tables with all the features which nobody sometimes needs to use, but has to incur the cost of going through them. So if all you need is a knife that excels in slicing English muffins out of this giant Swiss Army knife here, then that's what you should be getting. For example, if your requirement is just too much on 2 tuples, you shouldn't have too much on 5 tuples. To repeat that, one of the challenges currently with IP tables is that you incur the cost regardless. As we showed in the previous presentation, even when I had 0 IP table rules, I still incurred the cost in the CPU. I don't think even static hooks in our approach should be needed. Usability, like I said before, someone who's an expert at IP tables, IP set, and contracting should be able to comprehend and operate Ptables. Has someone tried to do this before? Indeed, the challenge with performance on IP tables and NetFilter in general has been an ongoing battle for years. It's got some great features, very usable. You can find anything you need on the Googles, but the problem. So there are 3 efforts that we are aware of. One is by Fulvio Risso et al., which he presented in Montreal, I believe, in Netdev 0x15. His approach was he's going to intercept IP tables. He's going to modify libiptc. So when you type your IP tables command, he's going to intercept them, and then he's going to transform into eBPF. There's an effort called BPF filter that's in the kernel that has been dormant until recently, which shims into the IP tables hook in the kernel. And then after intercepting the call into the kernel, transforms it into an eBPF backend. There was also an eBPF a suggestion during that heated discussion from Harold Welte, who used to be a maintainer of NetFilter, saying, hey, why don't you just extend IP tables binary and add, let's say, a -e option, which will tell IP tables don't call libiptc, instead invoke this eBPF API. We've taken a different approach. Instead of trying to be evolutionary, we've added an extra R. So we're revolutionary in our approach. And the challenge is, how do you deal with maintaining IP set if you're intercepting system calls? All right. How long are you going to be able? Are you going to intercept netlink in that case? Yeah. So basically, the features just keep growing. If you shim into the libraries, do you want to keep up with libipset and libiptc? Are the NetFilter guys going to be held back in their progress because they have to accommodate you? That has never worked well for us. I mean, I tried to do TC interfacing into IP tables, and I would claim it's still a disaster. It's still there in the kernel, but it's total disaster. The other thing you want to look at is, okay, so you keep going. The NetFilter guys keep adding features. What are you going to do next? Are you going to start keeping up with NF tables, which is the next generation? Can you really keep up? So we believe this approach we have taken is the most pragmatic going forward. All right. So our current state is, like I said, we do eBPF. It's based on Red Hat 8.3 at the moment. So any new features in the eBPF or in the kernel that are not backported to Red Hat 8.3, we have not exercised. We have a common interface for both XDP and TC eBPF, and for many reasons, we ended up using Clang 11 for at least up to this presentation. That seems to be working well for us. Let me go over the design a little bit here. Our initial design looked exactly like the abstraction. If you saw the abstraction initially, so actually the design started with just TC. That was our original goal. We'll do TC ingress and egress, and so. In other words, the priorities are essentially just TC priorities. Every rule set essentially maps to a single TC priority. Over time, it became clear that we needed to support XDP, and XDP does not have this concept of prioritization or multiple programs in the same manner that TC does. I like the TC architecture. Unfortunately, XDP is missing it. So what we ended up doing is improvising, and we built indirection tables inside the eBPF program. So what you're seeing here is essentially a map of, so it's an array of, let's say, LPM tables in this case, an indirection table. So when a packet comes in, we iterate the array and then find the correct table and then do our match on that table. We basically hit a snag with this. It became very more than complex to deal with wildcards when you're missing an entry. It was a waste of resources to have a wildcard where you have an entry with, you build a whole lookup just to find a match. So our solution at the end was to get rid of the tables altogether if it's a wildcard, and the control plane started getting complex. So we innovated a little bit. After some iterations, it became clear that there's one piece of information that was omnipresent, and that is the application details. So anytime the source, the protocol, the source and destination ports were always present. So we reorganized our data path, and so the first thing we look at is the source, the protocol and source ports. We group them together, and we have the ranges and lists in the same table. So if I was to go if I was to walk through a packet flow, then the first thing that happens is we must parse the 5 tuples: source, destination, IP, protocol, and port. And then the packet goes through the loop. This is a loop here from 0 to n-1, where n, and then we have n, which is the default. If there's no entry, we just skip it. If there's an entry, then we would remember the index we got there. So here you go. Metadata includes the 5 tuples that the parser extracted plus the priority and the packet data. We then use the priority that was extracted here as a foreign key into the next table, the next indirection table. There was always, the control plane always ensured that was the case for any rule set. They will always use the same index. We'll then, if that LPM was present, then we would try to match it. If it was absent, we would skip it and just jump to the next indirection table, where we search the destination IP in the tables. If there's a match, we'd proceed to declare victory that we have matched the packet at that point. If there is no LPM table, we'll skip it. And if there was no match at any one point, we'll go back to the loop again and continue iterating this loop. I hope that was clear. We can talk afterwards if there was some questions. Our semantics, like I said earlier, we have a simple C-based CLI tool called, you guessed it, Ptables. And to compare against IPset, this is how you would create an IPset table by saying create, and you provide the table name, and the algorithm we used was the hashnet, which allows for prefixes. And let's say in this case you only wanted 10, and we always wanted counters. This become aggregate counters essentially. And in the case of Ptables, we say just create table itable1. So someone familiar with this will not find it very difficult to adapt to that. And then you start adding prefixes to that table. And so as you can see here, we're adding multiple prefixes into itable1. And I left the name here to be the same as that so that you can see how we would do it in the case of Ptables. So Ptables has a semantic. The only major difference is we have to specify tables because we also have rule sets using the same binary. And we'll likewise add prefixes the same way. So once you create your groupings of LPMs, you then need to create the binding into rule sets. And so this is how Ptables would do it. You specify the set. In this case, table 9, itable 9, for example, we're doing this on ingress, and you match, you use that for the source and use itable 6 for the destination. Port ranges of 20,000 to 25,000 for the source port, and destination port singular 8080, and accept. Because of Ptables bin or Ptables, yes, we use explicit priorities, so it's not just an append. You can just specify where you want it inserted. And the -i is equivalent to the dev here. People familiar with TC semantics will recognize this. The input essentially maps to the ingress, and the semantics here are very similar. So likewise, this is how you can see the for example, this is how a list will be defined, and this is how a port list will be defined. We can talk about this afterwards, but the point I'm trying to make here is we have equivalent semantics. We think that these are sufficient for someone who's a craftsman at the trio to be able to follow. And more importantly is we have a single tool. We have Ptables for both groupings as well as rule sets. All right, so I'm going to now go over the challenges. I have to move fast. I'm a little behind, I feel, at this point. We should be so the biggest challenge was tooling, really. A huge amount of tooling. Remember, this ran over a few months, and kernels evolved, Clang evolved, libbpf evolved, the verifier evolved. So it was reminded me of the old days when SLS was the distro of choice, or you could go and craft your own Linux distro using Ptables that you may or somebody else may have built. There's no such thing as an eBPF super packaging that exists today. So having said that, I believe the tooling has improved. It's not there yet. It's not ready for the faint-hearted. There's lots of challenges when you run into a problem and you see some message that the verifier spews. You're not sure, is it the kernel? Is it the compiler? Is it the verifier? Lots of little surprises, like, you can't build a kernel unless you upgrade PowerHole, which is a shocker, just so that you have BTF support. There's multiple issues with IP-Route2. I have to give kudos to libbpf. I think it did excellent. It's very well maintained. I'm very happy with the approach it's been taking. The verifier challenge, I'm going to go a little bit on the some of the verifier challenges and the compiler next. So let me just list a few challenges with the Clang here. There are many, but my memory just remembers the latest ones. So I have to say, we never trusted the compiler in the earlier days. So that's how bad it was. We ran into bugs in different versions. The most recent one being the one I'm listing up here, where if you declare, let's say, int I equal to 0 and try to use that as a key, then the compiler was generating bogus opcodes. Of course, you never find out until you try to load the program, and then the verifier complains. Typically, upgrading the compiler, you're good. Building Clang has vastly improved. That link that I provide here is a lifesaver on how to build Clang. I think the LLVM guys have really taken it up a notch. And one of the little surprises that sometimes it works, sometimes it doesn't, is if you build your user space code with GCC and then your kernel code with Clang, and it may never work, actually. And you probably will have a very difficult time understanding why. So always try to keep to the same versions of Clang for both kernel and user space. Verifier, yeah, when we started 4K was the state of the art for instructions. Very happy when we saw 1 million instructions, which is likely for us supported in Red Hat 8.3. One of the challenges we found is that using BPF to BPF calls is usually a burden for verifier messages. So we, instead of just inlining everything, we forced inlining of the whole program through that Clang option. Inlining makes calls inline. I have to point that you don't always need to make inline, but we want to get rid of that bother. So just as a reminder, yes, we needed loops because we have to iterate linearly the rule set tables. The loops were missing in the earlier kernels that were tested. So our initial, like I said, we started with TC priorities. We need to worry about this, but of course we had to move afterwards to support XDP. So our initial workaround was with the Clang pragma to unroll loops. During those early days, we started hitting limitations with the size of instructions. And then around 5.3, which we found was backported, or is part of the Red Hat 8.3, bounded loops were introduced. And what we found was we were hitting the wall because of complexity, not of instructions. I'm going to go a little bit over this in the next slide here. It turns out it's not just about instructions, which is a very widely quoted limit. We got 1 million instructions. I had a program that had 3,200 instructions and was rejected by the verifier because it had branches in there. And the only way for you to find out that you are hitting this complexity issue is if you have to load the program. Introducing branches inside for loops is susceptible to path explosion. Then, of course, when the verifier fails, you get very unhelpful messages which point to just code that has nothing to do with the issue. Essentially, this was before we became experts at dealing with verifier. Before we created our bag of tricks, this was extremely poor development productivity. It still is, but now we are wiser, so we know what needs to be done when we see something that doesn't make sense. We have a list of things we check. So overcoming challenges and loops and code complexity. Yes, we need to support a lot of rule sets. We can't do it if we have if statements inside the loops. So what we ended up doing was we ended up creating an array of programs. That's the array of programs would be linear, like a linear graph that essentially we carry the loops. Now we, in addition to carrying the metadata and the packet data or the packet headers, we would also carry the loop state. So it worked well for TC. 20 bytes. Unfortunately, that thing is called CB. That threw me off for a bit, but it really is only 20 out of the 48 bytes that are available at eBPF. And we could do a lot of loops, a few thousand. I can't remember, maybe it was 4,000 to 5,000 at the time. That because we could, we didn't care about the 1 million instructions. I think our code was probably around 5,000 instructions per program. And, it was magical that you could do 32 programs. That's the upper bound on how many programs you could have. And in theory, support up to 32 million instructions as long as they're not linear. So it is feasible, perhaps, to take the code and create a lot of instructions and unroll them. Basically, do a loop unrolling and just not depend on the branching. But that's not the approach we took. I'm sorry. I'm going to talk a little bit more about it afterwards here. So same. So the idea of having the same code base for XDP and TC resulted in us going back to the drawing table because you don't have the CB structure in XDP since you have linear buffers. So our obvious answer was, yeah, for XDP, what we're going to do is read and write into the context metadata area which exists. And to our shock, we saw performance going down to at minimal 10% went down because of cache issues. I'm not going to go into those details right now, but we can have a conversation after. So back to the drawing table. Okay, so we borrowed an idea from Fulvio Riso, where he carried the metadata in a per CPU table. And this works okay because the BPF program runs to completion. It meant writing multiple reads and writes to the different tables, but to the metadata table. But it was okay because it was not as bad as 10% or more loss in performance. So it turns out we can do recursion as long as we restrict our recursion to 32. So what we ended up doing is instead of having an array of 32 programs, array had only one program, which then invoked itself and carried the loop state so you don't have to replicate the code. So the earlier program, the earlier packet flow that I showed applies. There's still little gotchas here and there in how we keep track of what's the most optimal loop size, for example, in the recursion. So we have some parameters which, unfortunately, at this point are compile time parameters that define what the loop size should be. Challenges on global tables, as I said earlier, we needed to have per direction, per port, or per group of ports tables. So what we ended up doing is basically naming them at compile time. So there's a compile option which says I'm building these for this following ports, and when you list them in the pinned path, you'd see a suffix that has the port name, right? I believe this could be fixed if we build the tables a priori. before we loaded the program. And the new BPF TC API discussion that went south a little bit could be very useful as long as it accommodates for these requirements that we have here. Currently, I think we can do that with XDP. Challenges with maps of maps. You cannot have heterogeneous map of maps. In other words, you can't create an array of maps or a hash of maps and then have it point to different types of maps. Could be used as an optimization in some cases, but that's not how it works. So we essentially you can only have an indirection table for LPMs only. And you also can, even when you have only LPMs or other types of tables, they have to be of exactly the same size. This was a bit surprising to me, that, all the tables, if they are size 10,000, then the second pointed table has to be size 10,000. The other thing is you cannot create just in your program, boot up and have a map of a map with no entry. It has to have at least one entry. Common trick is to delete it. This will be tricky to figure out because I couldn't find any examples that say this. It turns out this worked okay for us because we needed a default table. Performances, another one that was interesting, which is gives meaning to clever optimizations could bite you. We started by having a hash table as the indirection table, and then as our performance was not as great until we changed it to an array, and then we gained 20 to 30 performance improvement. Now you have to observe that we have a lot of these tables, right? Per packet, there's at least 3 or 4 of them. So while hash may look cheaper to you, arrays work a lot better, and we have no problems with RAM. We have we have greater than 100 gigs of RAM. Next, we introduced hashing. Basically, so that's our next level of optimization. Is let's start introducing hashing, and this is how it looks like. We can go over this afterwards. We had some challenges in hashing, right? So the most useful hash scheme that existed that was management free in eBPF is LRU. Unfortunately, there's problems with LRU because it doesn't meet our path flow accounting that we need. It tends to evict entries that have least been used when the table overflows. It tends to trash if not properly commissioned. And we have a desire, which I should probably have mentioned earlier, that we want to pin certain flows, let's say, that have very high latency, so low latency requirements to the cache, that they will never be evicted, and this is almost impossible to do the LRU. And of course, the management part of it. It's tricky. If I update a rule set, how do I go now and flush the cache? The control over that is a bit tricky. So our approach was to overcome the challenges. We invented our own caching scheme, which can pin flows so that they're not evicted. It does flow accounting. Eviction on a rule set is, at the moment, brute force, flush all the cache. How we deal with the cache being full is we have a flag, which is called cache is full. When the cache is full, the event is sent to user space. Daemon looks at it and starts pruning or garbage collecting cache entries when it's necessary. And at that point, no new cache is created. Everything that doesn't match goes through the slow path essentially until the user space daemon resets this. There are other challenges with XDP that have been discussed in the XDP workshop. For example, I'm not going to go over them here, but it's not at par right now with TC. Makes TC a lot more appealing. I'm just going to go over the potential future works as I've essentially run out of time. We're going to open source this code. We're looking to write tools to convert from IP table semantics to Ptables. We don't have support for fragmentation right now. Our test infrastructure does not have this. We're in the process of adding bidirectional state. IPv6 support is for the future. Our requirements currently don't require IPv6. There's potential for supporting other OSs, Windows, the BSDs. We are in the process or have started initially doing a Rust-based control plane. Yay, Rust. The Windows verifier seems to be a lot more robust than Linux. They do abstract implementation instead of pattern matching, which has a potential to lead a lot more performant BPF code. So I've run out of time, so I'm not gonna go into details about that. Let's have a discussion afterwards. Acknowledgements. This work was helped a lot by Paul Menini and Pedro Tamela. Without them, the evaluation of this would have been very difficult. I would like to point to the references, the images we've used here, and now I'm ready to go to Q&A. Thank you.
All right. If you have any questions, just post them. Thank you. Thank you. Okay, you guys, come on. Come on. Stop it. Stop it. All right, enough. Come on. So I'm going to post the first question, which is from Talk. There you go. If you want to come on stage, just raise your hand. Talk. So he says in the IP set example, I was using a hash map type, but your eBPF program used. So IP set was using the net map type, so which is the closest equivalence to LPM, which basically allows you to add prefixes. I don't know if that answers your question. So we translated it to LPM map types. Actually, initially we started by using the hash map type called IP, but we ended up realizing we needed to support a lot of prefixes. We did not, so LPM hash map was not a big bottleneck for us. I mean, there are other low-hanging fruit, so we haven't really visited as where the LPM hash map was a problem. I think at one point, the maximum we had was anywhere from 50 to 60 entries, so maybe we haven't hit that point yet where it becomes a problem in performance. Does that answer the question, Talk? Just send me a thumbs up there, and then I know I answered the question. Or you can go on stage. All right, thanks. Next question is from PJ, which I'm going to now put on the stage. Would something like a verifier outside of the eBPF loader to look at code branch explosion be more helpful? If yes, will this be useful to suggest to eBPF maintainers? Absolutely. I think that from a developer productivity development, that cycle where you're trying and then loading and then failing, oh shit, it failed. What the hell was it saying? Why did it fail? Damn it, must be the compiler. No, it's the kernel. No, it's the verifier. I think if you had the verifier in user space, and I believe Microsoft has it in user space. I could be wrong. Last I looked, the approach that Microsoft took was in user space. And you have to remember also that the path explosion is because of the approach that the Linux kernel verifier took. As you know, so that's the difference. I think the approach taken by the Microsoft version, which I was told, if I didn't see that, but apparently they did post a lot of these comments initially to Linux, but it didn't seem like they got any feedback. So they ended up perhaps using their own version. But yes, this would greatly improve the developer productivity. Thank you. If you want to come on stage, I can put you. Just raise your hand again. There is a comment from David Arhen. He says, I'll show the comment on stage as well. I don't know if that comes out nicely there, but I see it right at the bottom. He says you can create maps using, say, BPF tool with the name you want, then replace the dummy name in the program with the created one. So we could. So would this work with TC Loader? I mean, we're going to move away from TC Loader if the BPF version actually meets our requirements. Are you willing to speak to that, David, or anybody else? If you, I can bring you on the stage. Do you want to come to the stage? Try to invite you. Just click on accept if you want. But yeah, the TC Loader works differently than the Okay, there's David. Okay, good. Yeah, I can hear you.
You can hear me?
Yeah, I can.
So yeah, so I was playing around with that last year with the same programs being loaded on XDP and TC. You just have a front end that converts the context to the different context you're given, right? But that same trick exists where you create the maps and then you replace them, right? Because you don't want to have to build and manage programs with instance-specific data, really.
Yeah. It's very
so
painful.
I sent you a reference, and I'm looking for the TC version of it. But yeah, the one I sent you was XDP related, and it's from the talk I gave at last year's conference related to forwarding with virtual machines.
Right. Okay, I'll go back and review your talk, and thanks for that tip.
Yeah.
Okay. Another question here. So, do you have any other commentary, David, or I'm going to remove it from the stage? There's a comment from talk that I'm gonna.
No, I'm good.
Okay, thanks. Here's what talk is saying: there is no user space version of the Linux kernel verifier, and using any other verifier will not be semantically equivalent. So it will not be terribly helpful, sadly. I think you may be right. But I think I've seen efforts, and somebody correct me if I'm wrong, that some people have tried to take the kernel verifier and put it in user space. It's mostly academics trying to do formal verification kind of activities. The challenge will be upstream, right? I mean, how do you move it upstream? I mean, we had thought about, in order to, we actually did consider this, by the way. We did. It's just, we haven't had time to proceed that way. And why don't you come on stage? So, talk. Why don't I invite you here? Because you have a lot of other commentary there. Is it okay? I'll just send you this, and you can join. All right. Yeah, go ahead, please.
So on the verifier thing, it is theoretically possible to integrate loading the program into the kernel into your build system using a VM. Like we have the CI systems for both libbpf and libxdp will run tests in a virtual machine using virtme, I think it's called. So you could theoretically put that into your build environment and get instant feedback.
That would be great.
It's a bit cumbersome, but I think it's suitable. You can also do, there's also the possibility to do proc test run stuff from user space so that you can execute the program and actually test it as a kind of unit test thing from user space. So you don't have to load it onto an interface and pass traffic through that, but you can supply a context object. And I think for the networking programs, you can even supply packet data, and then you will get just executing that program in the kernel using the test. So that could be to work around this.
If you have a reference there, just send me a link. Look, if it's going to be on CI, we're happy because that's a robot doing work, not humans, right? The problem is human productivity.
Yeah.
Right.
The other thing for TC was just another trick that's not that well documented. So obviously you can just use the TC support in the recent versions of libbpf, but if you don't have access to that, it is possible to get TC to attach the TC command line binary to attach a program that's already loaded into the kernel. So you can load the program using BPF, and then you can pin the program itself in BPF, and then you can get TC to attach the program from there onto the interface. Okay.
So we do a lot of pinning. We pin every table as I showed in one of my slides. So we'll give this a shot. So as it stands right now, we just it's a compile time option, and hopefully in one system you never change. But yeah, it's very unpleasant. We're also hoping that the whole libbpf TC integration, that whole thing goes goes peacefully and we get the solution that works for everybody. Otherwise, we're sticking with TC for now, the TC loader. All right, so David, okay, any other commentary, talk?
No, that's fine, thanks.
Okay, thanks. There's a comment from David. He just said he sent, we'll try to post the links to all these things. He says he sent an example. Okay, yeah, so that's in your email, David, I'm assuming, right? Thumbs up if yes. Yeah, okay, and we'll make all these details available. Maybe it's going to be on the website that where this presentation is at. And unless there's any other questions, oh, there's a QA. Sorry, I'm sorry, I wasn't paying. Wow, okay. So here's Ivan with a question as to how are you testing your eBPF codes in terms of added latency performance. So we have not touched VAT.io. We've just been using real devices on bare metal right now. Yes, we have automated, but a human starts these tests, and then when they're done, we have graphs of all sorts. And then when we see something odd in the graph, we can dig deeper into the data we've collected. So we have perf outputs, we collect port statistics, we collect a lot of stats from everything you can think of that's useful. Port statistics, socket statistics, if we're running host level stuff. We never look at that. We like never to look at that stuff unless it's important to go back and take a look. We've kind of trusting the system we're building with, but we always sometimes intervene and do things manually. I hope that answers the question. If not, if yes, send a thumbs up and thank you. Did I miss anybody's question? No, there's anything on the chat there. Paulo Benny says, okay, so there's a couple of commentaries in case people are not watching the chat. There's one from Paulo right there. We're saying, oops, did I post the right one? Maybe I'll post this one here. User space verifier or about somehow wrapping UML. Okay, and there's a response from Talk that yes, you could do that and probably prove that your program is correct. The problem is that if the in-kernel verifier doesn't agree, you're still not going to be able to load the program into the kernel. And that was it. Okay. If there's no more questions, I'm going to end the session right now. We are like 2 minutes into chewing into the next talk session here. Everybody show up to that. It looks very, very interesting. I'm looking forward to attending the next session. Thank you. Thanks. All right. Thank you, everybody. We're going to wrap it up here.